All right, steel structures. Let's do this. Leroy. Thank you. I have outdated references all over the place. Steel construction comes all different formats: moment frames, brace frame buildings, pre-engineered light frames, combination of steel frames and concrete shear walls, steel framing with URM infill. I'll have us get to our steel portion of our field manual. Anyone have a page? 67 on top of it. So here's our steel structures. Has a lot of the same depictions. Here's type S1 steel moment frame buildings. So you can see these isometric blowups and some of the similar checks. Moving to page 70, overall damage, floor and framing, columns, vertical, horizontal, diaphragms, moment frames, foundations. A whole bunch of detail. We're not going to get through all the details of it, just kind of some high-level things. So the real fundamental challenge with doing post-earthquake safety assessments of steel buildings in particular is this is what it looks like hypothetically in this cartoonish drawing. We have our columns, we have our beams, bolted or welded shear connections. For a moment frame building, the ends of the beam, namely the flanges at the top and bottom of the beams, are welded to the column. That's what gives that sort of table-like moment frame, or the right angle wants to remain a right angle. We have a concrete slab on top of it. So that's what it looks like in theory. Sounds good. We're going to inspect it. That's what it looks like when it's constructed. There's a beautiful steel moment frame there. Then we cover up in fireproofing, because if we have a fire, we don't want the structure to collapse. Then we cover that all up with finishes, architectural finishes on the exterior and the interior. So it can be a real challenge to actually get to the steel structure, steel moment frame in particular, but the steel structure in general, to do a very thorough observation of the actual structure. So a lot of it, you're deducing what you can from what you know about the context, when the building is built, what kind of seismic design and detail and requirements, if it was built in the 60s or 70s versus 80s or 90s versus 20s and 10s, whatever we call them, very different expectation for what we might anticipate the build seismic performance to look like. We talked about pre-Northridge moment frame buildings. That was because we effectively discovered from that earthquake that the welds, the connections, this is not projecting well at all. That's okay. The connections between the beams and the columns ended up having very brittle welds, even though we think of steel and welds in particular as being sort of ductile things. Cracking often would occur based on a bunch of the details of how they had backer plates and put the welds into sort of multi-axis stresses that ended up being brittle and creating fractures like that. Now, how hard is it to get to that beam column joint to observe that crack? Very. You got, assuming this is an office building, you got your suspended ceiling system at 9 or so feet. You got to get through that, many more feet of ductwork to navigate through, clean off the fireproofing. This is really a challenge to get to the structure in this type of instance. Here's some other just depictions of brittle failure of steel. Here's an old riveted, built-up column that they had to demo a whole bunch of gypsum wallboard framing to get access to. Here's a hospital over in Bremerton that we've done a bunch of work on retrofitting that we did engineering evaluations that I referenced earlier in order to get up in the ceilings of these 16-foot floor-to-floor moment frame constructions to observe welding damage. So that's moment frames. They're less frequent, so ideally newer moment frames will perform pretty well. Pre-Northridge moment frames before 1994 can be brittle, so just pay attention to that if you're called upon to do a moment frame steel building. Steel brace frames, as Rami discussed, rather than the connection and the stiffness of the beams and columns, is that diagonal brace and cycles of compression and tension, various types of configurations that give it its lateral resistance. There's a couple of different configurations that are most common: single diagonal, like that, double diagonal or X framing, chevron, which is this sort of upside down V, and an eccentric brace frame where we expect a lot of the ductility, the nonlinear behavior, the yielding to occur in this little link between the side of the brace and the beam and the column itself. So a couple different configurations. I think I have some videos just to help think through the cycles of tension and compression. So ideally, our braces, this plane. So that's not what we want, just to be clear. Ideally, we want our braces to buckle, kind of globally absorb energy and compression, stretch out in tension, and have the proportions such that they don't yield and fracture catastrophically like that. So really what we're aiming for is something more like on our left. It's still damaged, it's still absorbed a lot of energy, but it's done it in a very particular controlled manner rather than something like what we saw in that video, or even on the right where we have local buckling that sort of pinches, and its ability to absorb energy is much less. In the depiction in this full-scale test that was performed on the right compared to the one on the left. So basically the one on the left is what we look for, what we design for, and we even designed the connections to accommodate that type of out-of-plane global buckling of the brace rather than local buckling of the walls of that particular brace. So when you're doing a brace frame inspection, looking for the performance of the overall brace and then the connections themselves. The paint here is specifically designed to sort of fall off so you can see where the yielding is, so where the steel plates have gone past their elastic state. And you can kind of see this elliptical behavior here on this gusset plate. You can see some of the welding connections. You can see some buckling from the beam that this gusset plate is connected to, and not ideal, but you can see how it fractured because it wasn't able to accommodate the out-of-plane deformation. So all things, if we're doing a steel brace frame evaluation to look for, and ideally it's more ductile than that. Was there a comment? Just talking to yourself, it's okay. Steel frame construction, here's just some more depictions of it. Again, it's just like the moment frame examples that we looked at. Some cases we have access to visibly observe the structure itself. In many cases it's covered up by fireproofing and or architectural covering that make it really difficult to access and observe. Here's some examples of visible brace frames that were apparently not damaged after the Anchorage event in some schools that we did some assessments of, but there was some depiction of movement as expressed in some of the architectural finishes. Some more examples of that. Here is actually we haven't filled out a placard yet, so let's fill out a placard for this building, but let's first talk through it. So this is one wing of an airport building. This is also in Santiago, Chile, following their event, and it just happens to have exposed chevron configuration, concentric brace frame. To circle back to our conversation. This is what it looked like from the exterior. There was not the failure mechanism that we were looking for, so there was out-of-plane buckling of this gusset plate and not of the brace as we expected. Fortunately, I guess fortunately is maybe a weird term, but after about 2 weeks, they were sort of quick retrofitting it to be able to get the essential port facility to be back in operational, to get people back in their terminal, because the whole thing is operating out of a tent facility. Tent facility here, I forgot my radius. So some in-plane gusset plate buckled and perpendicular gusset plate added. So since we haven't filled out a placard, I guess, first of all, what's the building occupancy type? Yeah, airport. Airport terminal, high occupancy. What's the structure type? Chevron configuration, steel brace frames. Now that they've retrofitted it, what's the hazard? I suppose that won't have the same performance as before, but they've retrofitted the non-structural systems. Let's stick a pin in the placard. I don't think it makes sense for this one. Let's just ad-libbing a little bit, but as I keep going through steel. Here's steel light frame. This is typical of what we call PEMB, pre-engineered metal buildings. A lot of our light steel buildings will have this typical construction style, which has tension-only braces in one direction, and essentially a steel moment frame, the steel bents that are very refined in their engineering to be cost-effective ways to put up storage units and things like that. So this is S3 light frame building construction. And the thing to consider with tension-only frames, so you have these rods, so they work in tension, but like the spaghetti that Rami mentioned, not very well in compression. So each direction has something. But after you go through one cycle, it's stretched out, and so in the next cycle, you have to go a little bit farther before it engages. And so pretty quickly can drift quite a bit. So here's a depiction of that through some testing. Yeah. The rhythm there, I thought Rami was about to start spitting some bars here. I was feeling it. But you can see how it pretty easily gets to very high drifts because it has to go farther and farther before it engages. So in many cycles, you can get, to use a technical term, there's pinch hysteresis loops where it's not necessarily absorbing that much energy because of the amount of deformation required. The nice thing is after the fact, when you find these PEMB buildings or tension-only brace frames or tension-only rods like this one that have elongated and stretched out, they could be fixed relatively easily by just tightening it back up more or less. So that's not uncommon. Here's some depictions of those elongated tension-only rods and those types of buildings. The other thing to pay attention to, though, is not well-detailed buildings of this type can sometimes have those rods connected directly into the column, not at the base level, but a little bit above, like this depiction here. And so rather than putting the force from that rod directly into the foundation, you can very easily buckle that column, and now your vertical load carrying capacity has been compromised, and the whole thing can be suspect. So one particular thing with PEMBs to look for. Some examples of steel building damage from hurricanes. Kind of plow through this for the sake of time. A whole number of them. Steel frames with concrete shear walls, so this is sort of a hybrid system where you have your concrete core wall and your steel frame outriggers, and they're working together. Steel frame with infill masonry walls. This is more just getting acclimated to some of the different configurations of these. This is sort of a certain era of building where they're building with steel, but also still infilling with masonry. So that's all I got for steel. Kind of punted a little bit on some of it, but at least you're a little bit more familiar with some of the configurations and terms.